Okay, what we have here is on the right we have the problem, which we want to minimize, and on the left we have a working space for doing all the calculations on the graph. So we're going to do the entire algorithm right now, and the title here is Network Simplex on Graph. And we're just going to make some notes here. We need to distinguish between the basic arcs. And for the basic arcs, we have that f minus t is less than or equal to a CFT. Sorry, for the basic arcs, it's equal to CFT. And which means that either f is equal to t plus CFT if the from node is known, or t is equal to f minus CFT. And this is if t is known, and this is if f is known. So that is the title for that. And for the non-basic arcs, where we need to check feasibility, we have that f plus t needs to be less than or equal to CFT at lower bound, and f plus t, it needs to be greater or equal to CFT at upper bound. And we'll keep this space here right below the below the diagram, but there really aren't that many calculations that we need to make that are not on the graph. So to begin with, we need to know what the initial basic feasible solution, and we'll go with the same one as we had before. And if you recall, we had 30 units flowing here to satisfy W1. We had done 20, which is the rest of the 50. We had 40 here, and we had 60 here. So this is a spanning tree, all within bounds. Conservation of flow is met. The first thing that we need to do is to determine the dual variables. And those dual variables, there will be one value for F1, one for W1, DC, F2, and W2. One of those can be assigned arbitrarily. So we can say that 0 is assumed arbitrarily. If that's the case, we know the from. So now there are two arcs here, and we can only use the basic arcs, only the ones in green. So DC is going to be 0 minus 400, and W1 is going to be 0 minus 900, and DC to W2, again the from is known, so the 2 is equal to minus 400 minus 100 is minus 500. And for this case, the 2 is known, so the from is equal to the 2 plus the CFT, so that is equal to minus 400 plus 300, so that's minus 100. We now have all of the nodal prices, and we don't need to make any size. So this part was easier doing it on the graph than we had before. The next thing we need to do is to determine any infeasibilities. So we have three nodes. We have F1, F2. So let's check that. We can just say F1 minus F2 is equal to 100, which is less than or equal to 200, so that's feasible. We have W2 minus W1, which is equal to minus 500 plus 900 is 400, and that is greater than 200. And so this is a problem. Not a problem, but that looks like that's going to be W2, W1 looks like it's going to be the entering arc. And finally, W1 minus W2 is going to be equal to minus 900 plus, so it's minus 400, which is less than 300, and so there's no infeasibility there. So this is the entering arc. So for the entering arc, we can pull out our green pen, and we can make this then W2 to W1 is the entering arc. We want to increase it as much as possible, so this will go plus, this will have to go negative, this will have to go plus, and this will have to go plus. And what's the most that we have in this loop? Again, this is creating a loop, and we have to then change the numbers to get rid of the loop. So the most this can go up by is by 20. So this goes up by 20, and if that's the case, then this goes down to 10. And this then goes up to 40. And this goes up to 80. And we're at the limit, which means that the arc is no longer basic. We can also get rid of the little plus signs, minus signs. That wasn't intended. Okay, so there's no more loop, and so we're at our next iteration. Well, if that's the case, let's check. We have a spanning tree. It's connected, and there are no loops, and conservation of flow is maintained. 40 and 40 is 80, 20 going that way keeps 60 at W2, 10 and 20 keeps 30. Everything is in order. So the question is, now that having done this, well, let's not erase anything here yet. So you might be tempted to erase all the prices at the nodes, the dual prices, but that's not necessary, because it only changes if there's a change. The change is that DC to W2 is now no longer green. It's no longer basic. Which, let's check. F1 is still 0. There's nothing changed. So W1 stays at minus 900, and DC stays at minus 400, and F2 stays at minus 100. But W2 can no longer be calculated based on DC to W2. It has to be calculated from W2 to W1. So we know the 2, so the from is the 2 minus 900 plus 200. So this is equal to minus 700. Let's look at that again. W2 is equal to, we know the 2, which is minus 900. So minus 900 plus 200 is minus 700. So that's the only value that has changed. So that again is simpler on the graph, because we don't have to recalculate. We only have to recalculate one number. Now when we come to determining feasibility, well, we still have F1 minus F2 as before. Nothing has changed there. We have W2 minus W1. We have now a W1. No, that the second one is no longer, this here is no longer the item that we have to deal with. Let's see W1 to minus W2. That still is the same, except it's now minus 900 plus 700, that's minus 200. So this gets changed to minus 200, which is still less than 300. So that's okay. But the new non-basic arc, which has to be checked for feasibility, is DC to W2. But DC to W2 is at its upper bound. So since at its upper bound, we need that F plus D. So we're talking about DC plus W2, which is equal to minus 400. So that's 300. Has to be greater than, which is greater than 200, because it's now at its upper bound. And that means that all of this, we now have the optimal solution. So the algorithm is quite compact. Once you use all of the results that we've used before right on the graph, and it can be implemented in code real fast.